Alright everyone, status reports. The head is operating fine. General heart?
Sir. Heart is in good condition. Blood pressure is 120/80. Could use a little bit more exercise, but otherwise pretty good.
Okay. Colonel Colin, how are things down there?
Twice a day and solid.
Private Pancreas? Where's Private Pancreas?
Hold the phone! Insulin productions are 75% and falling. And he just had a pancake breakfast.
Contact the glucose monitor ASAP. Set in the pump tank on the scene. Incoming glucose. Private Pancreas, on my mark, move out.
Sir, yes, sir.
Ready, go!
Oh, you okay?
This is crap.
Ma'am, you called?
Where is that insulin tank?
So let's take a look at what's going on inside our insulin tank. Insulin in a diabetic patient needs to be delivered at a constant rate that can be determined by their doctor and by algorithms to help manage their blood glucose levels. Insulin is delivered through an infusion set, which it uses a needle to penetrate into the subcutaneous tissue in either the back or abdomen of the patient. This infusion set is then attached via a tube to a syringe, and the syringe is then placed inside an insulin pump. The insulin pump houses an electronic motor that is used to drive the syringe, therefore pushing insulin stored in the syringe through the infusion tubing and back into the patient. There are different lengths of tubing depending on the user's comfort and the user's need, and also the size of the user. Children obviously would require smaller tubing. 31 inches is an average tubing length. For our interest, as engineers, we would like to calculate how much force we need to apply to the syringe in order to put a constant rate of insulin out at this end. The first step is to look at using the conservation of mass to determine the velocity that the syringe needs to move in order to output at a certain velocity. These velocities can be determined using the volumetric flow rates given to a typical pump. These volumetric flow rates are the lowest and highest achievable by the pump. The highest achievable is due to the electronic motor in the pump's highest rate of speed that would also be deliverable to a patient safety-wise. The lowest rate is determined from several studies that have shown that crystallization of insulin can occur at any volumetric flow rate that is below this recommended level. The inner diameter of the infusion set and the syringe can vary by pump, but we've chosen two inner diameters that are very typical to certain pumps in the US. We can determine the velocity at point 2 using these two volumetric flow rates. Knowing that, and knowing the internal diameters of both the syringe and the infusion set, we can calculate V1 using the conservation of mass law, A1V1 equals A2V2. Given the volumetric flow rates that we have from our studies, we have determined the highest and lowest velocity rates in insulin care and diabetes care. The volumetric flow rate is often used in units per hour. 100 units is equal to 1 milliliter. In order to achieve these numbers, we did do some unit conversions, which we will skip over in the interest of time. Once we have V1, we're able to use Bernoulli's equation to calculate the change in pressure between the two stages. Now that we know the velocity in section 1, we can calculate the pressure in section 1 using Bernoulli's equation. P2 was found to be 294 pascals in literature as the subcutaneous pressure. Using Bernoulli's equation, we can eliminate the change in potential energy by assuming that the height between the insulin pump and the infusion site set on the patient is insignificant. Knowing V1 and V2 and P2, we can rearrange the equation to calculate P1. Because of the very insignificant difference between V1 and V2, P1 is very similar to what the subcutaneous pressure was found to be in literature. Knowing that pressure is force over area, multiplying the pressure found in V1 by the area of the syringe, we can calculate the force required to inject the insulin into the patient, which is approximately 0.024 newtons.
Where is that insulin tank? Now that everything's settled down, Private Pancreas, good to see you on your feet. What are the updates?
Ma'am, insulin levels have stabilized.
Yay!
That's a shit job.